Right, a positron is an anti-electron. Okay, it's an anti-electron. So an electron is basically got a charge of -1, and it is known as a lepton. Basically means it is a very light in terms of mass particle. Now a positron has got a positive charge. Okay, so you can write it down as E+, and it is an anti-lepton because it's antimatter, the exact opposite of an electron. It is an anti-lepton, so its value is it's got a lepton number of -1, whereas an electron has a lepton number of 1. So it has the same charge. Well, no, they've got different charges. I guess that's wrong. It has the same mass. That's correct. But let's just check the other ones. It has the same lepton number. No, the positron's got a -1 lepton number. The electron's got a +1 lepton number, so that's wrong. Same electric field. No, it hasn't, because obviously we know that electric fields go from plus to minus, so the field lines will be going this way into an electron, whereas in an anti-lepton the field lines will be going outwards, going from plus to minus, whatever's outwards. So D's wrong as well. The correct answer is B. What particles make up our antihydrogen atom? Right, well, hopefully you know that a hydrogen atom has got a proton and it's got an electron on the outside of it. So that is what hydrogen looks like. So antihydrogen, which is the antimatter of it, must have an antiproton, the opposite of a proton, and an anti-electron. So this is antiproton and anti-electron. So it has an antiproton and an anti-electron, also known as a positron. Right, how much energy would be released if an antihydrogen atom annihilated a hydrogen atom? Right, okay, so you know mass of a proton is 1.67 times 10 to the -27, and the mass of an electron is this. Well, the mass of the proton, so the mass of an antiproton and the mass of an anti-electron will be the same. So we need to get these two values and multiply them by 2. So 2 mass of electrons, 2me, plus 2 mass of protons will equal the following. Okay, so what we do is we get the mass of 2 electrons, which we've got here, and then the mass of 2 protons, which we've got here. And when we calculate it, we find it's 3.34 times 10 to the -27. You will quickly realize that the electrons are so light in comparison with the mass of the electron. They haven't really registered this at all. If you notice, this 3.34 is essentially the mass of the 2 protons. Now we need to convert that mass into energy, and in order to do that we need to use Einstein's famous equation, E equals mc squared. And so we stick in the values, which is 3.34. I'm going to use the values I've got in my calculator, which is 3.341822 times 10 to the -27. And I'm going to multiply that by the speed of light squared, which is 3 times 10 to the power 8, all squared. Now that's quite a small number, but certainly big considering that you're just using two tiny atoms. How much? This is saying how much energy, how much matter is needed in order to release that much energy. So we can use Einstein's famous equation, E equals mc squared, and if we rearrange this, we get E over c squared will equal the mass equivalent of 4.2 times 10 to the 15. So 4.2 times 10 to the 15 divided by 3 times 10 to the power 8, which is the speed of light. We need to square that, or squared, and when we put that into our calculator, we'll get an answer, which gives us an answer of 0.047 kilograms. So just think about that. 47 grams of hydrogen releases that much energy, the energy in a hydrogen bomb. Okay, so it's a huge amount of energy released from nuclear fusion. Right, okay. When it's the energy that a gamma ray photon carries is sufficient, okay, to produce matter. Yes, the energy it's got equals HF. So since gamma has a high frequency, it has a high enough energy. And of course that will turn into mass energy, so you can use mc squared, you can work out what it is, and there's sufficient energy there to be able to create mass equivalent to the masses of an electron and an anti-electron. It has to be an anti-electron because you can't create charge. So we've got -1 +1 means the amount of charge beforehand is the same, and you can't also create leptons really. You must keep the lepton number the same. So you've got 1 lepton here and you've got an anti-lepton here, and you have 0 leptons on this side. So 0 leptons equals 1 lepton plus an anti-lepton, which means that it's got a negative lepton, so that the lepton number is conserved. Right, for the pair annihilation, if you get these two together, they interact, they will actually annihilate each other. And when they do that, all of that energy is released in 2 photons, okay? In 2 photons, not the one, but 2 photons. They go in different directions. They sort of conserve momentum, because momentum has to be conserved as well. Each of these particles, the electron and the positron, have masses. They will have velocities. You can't destroy momentum, and the momentum is actually carried away by photons going in opposite directions. Right, we have to calculate the maximum wavelengths for each of the 2 gamma rays created. Okay, so the gamma rays will each have the same energy, and therefore they would have been created really from the energy from the mass of one of these electrons. So if we look at the energy of one of these electrons, we know it's going to be equal to mc squared. Okay, so there we have that, and we know that that's going to be equal to hf. Now we need to find the wavelength of this, so we need to choose c equals f lambda, and if we arrange that, we will get lambda equals c over f. We put this into this equation here, so now we get mc squared equals hc over lambda. Okay, so I can replace that. This of course should have been the other way around. I should swap these 2 around at this point here. Okay, so get hc over lambda. I need to find out the wavelength, so I rearrange this, so I now get the wavelength equals hc over mc squared, and of course that therefore simplifies a bit further to h over mc. The mass of the electron, well, let's do this. That's going to be, Planck's constant is 6.63 times 10 to the negative 34. The mass of the electron is, given it earlier on, was 9.11 times 10 to the negative 31, and the velocity due to light, velocity of light I should say, is 3 times 10 to the power 8. And when you put all those values in there, you would end up with the wavelength as being, you get the answer 2.4259. Of course, when you round that up, you get 2.43 times 10 to the minus 12 meters. Right, why is this the maximum length? Right, if these the energy, as we know, is equal to hf, and if you rearrange that, you get hc over lambda, so that as the energy increases, the wavelength goes down. So if the positrons and the electrons had kinetic energy beforehand, okay, their energy will go up and their wavelength will go down. So basically, in order to have a long wavelength, they need to be stood still, okay? And what we just worked out there was essentially the particles stood still, but we know very well they would have had some sort of kinetic energy, so their value of energy would have increased. It'd been higher than we've calculated, and that'll have the effect of bringing the wavelength down.